Hello, everybody, and welcome to our tour of the universe. Our apologies for being a little bit late today. We're experiencing some technical issues, but I'm excited that we can go ahead and get started. So welcome, everybody. My name is Jackie. I'm the Planetarium Programs Manager here at the California Academy of Sciences, and we are going to be taking our tour of the universe. Now, our tour of the universe is going to be 100% live. And it's a little different than maybe some of our other programs you might have seen in our planetarium itself. In the planetarium, sometimes it's kind of more like a movie. This is going to be a different experience, hopefully something that you might not have experienced before. Using our planetarium software, we're going to travel to the edge of our visible universe and all the way back home. Now, we started off looking at our planet, but we're going to go ahead and zoom on in relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And as we zoom on in, you can see kind of that yellow line. That's just showing the path of the International Space Station, or ISS for short. And the ISS is as far as humans travel out into space nowadays. You can actually fit about 6 astronauts on it at any one time. And it is the largest thing that we have built in space. Now, to measure it from one side of its solar panels to the other, kind of that long ways of looking at the International Space Station, it's about the length of an American football field, or I like to say, the Academy of Sciences. So if you have walked from one side of our building to the other, you have actually walked the length of the International Space Station. But today, we are going to go much farther away. We are going to see how far our human influence has gone. We'll see how far humans have physically traveled to space, how far spacecrafts have gone, and how far our human communications have gone as well. But for now, the ISS is as far as humans do physically travel nowadays, though there are plans in the works for that to change. And as we zoom on in out from our Earth, it may look like the ISS was plunging towards Earth, but that's again because we are zooming out and the ISS is much, much smaller than our planet. In fact, it takes the astronauts traveling around Earth only 90 minutes to orbit us once. So they're traveling quite quickly. And you can look for the ISS overhead at night. All you have to do is look online to see when it will be passing over your area. And what you'll be looking for is kind of a little bright star, but it's moving very quickly in a line. Now, there's lots of different satellites up there in space nowadays, so you do want to make sure that you're looking in the correct direction. And usually the places that tell you when it's going to be passing overhead at night will also tell you where to look in the sky. But we're going to go ahead and we're going to continue our journey. And we can also look at our closest natural neighbor. And I'm going to go ahead and bring up the path of that. And that is our moon. Let's go ahead and focus in on our moon real quickly and zoom on over. Now, the moon is as far as humans have traveled out into space. You can actually fit on, our astronauts actually went out here in the 1960s, and it took them about 4 days to travel to the moon. Now, even though the moon is our closest natural neighbor, it doesn't mean that it's close in human terms. The moon is about 250,000 miles away from our planet, and as we get farther and farther out today, we are going to be going distances of millions, billions, and sometimes even trillions of miles. And when we get this far out at these distances, it doesn't make sense for us to use kilometers or miles anymore as a measurement of distance. Instead, we are going to be talking about the speed of light as our yardstick, so to speak. It is the fastest thing that we know of. Now, if you were traveling the speed of light, which is almost 200,000 miles per second, it would take us 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away from our planet. But we can go ahead and zoom on in a little bit closer to the surface of the moon. And as we look at the surface, it makes it look like the moon has been hit by meteors, and maybe even some big asteroids. Not huge, but decent size. A lot more than maybe us here on planet Earth. But remember, the Earth is actually a much bigger target, so we get our fair share of impacts as well. The main thing to remember is that the moon has zero atmosphere, so there's no weathering, no erosion, and there aren't any plate tectonics for the moon to resurface itself, so to speak. But as we zoom on out just a little bit, we can actually start to see the full path of the moon around our planet. It takes the moon about a month to travel around just once, or I like to call it a month because it's not a full month, it's 29.5 days. And since we're seeing the path of the moon, let's go ahead and bring the paths up of some of the other objects in our solar system, planets. So you'll see the path of Earth as we zoom on out, and we'll start to see some of those other paths of planets. Now we have the sun in the center. Now, if we were traveling from Earth to the sun at the speed of light, it would take us 8.5 minutes. So we can say it's actually about 8.5 light minutes away from planet Earth. So we're not seeing it as it completely is instantaneous. It's kind of interesting to think about. But as I mentioned, we have the other planets in our solar system. If we're starting from the sun and we work our way out, we see the paths of the rocky planets, Mercury, Venus, Earth, and Mars. Further out, you can see Jupiter, Saturn, and even Uranus and Neptune. And when we start to get this far out, I like to kind of look back at our planet or our solar system and look at maybe some of the smaller objects in our solar system. Like this sizable gap between Mars and Jupiter, that's not empty. We have our asteroid belt. And we can kind of see some of those asteroid belts. Bring some of the other ones in. Now, I'm not going to bring all the asteroids up in our asteroid belt because actually, if I brought every single asteroid point up, it would crash my computer, and we don't want that to happen today. But instead, I'm probably showing approximately 70% of the asteroids that are known in our asteroid belt. Now, when we're this far out, I actually like to talk about an object that's inside that asteroid belt that's actually not an asteroid. And I'm going to go ahead and bring up its path. Might be a little hard to tell. I brought it up in this kind of lighter blue area. As we zoom on in, it might be a little bit easier to see. But as you can see, it kind of goes right through our main asteroid belt. Any guesses on what this might be? Well, if you said Ceres, you are correct. Now, Ceres is a very interesting object because, as I mentioned, right now, we do not call it an asteroid. We actually found Ceres first about 300 years ago, and at the time, we thought it was the only thing orbiting in between Mars and Jupiter. So we called it a planet. Then soon after, they started finding some of these small rocky objects in similar location that they called asteroids. So soon they realized, okay, maybe Ceres isn't a planet. Let's categorize it as an asteroid. Similarly, this is actually what happened to Pluto. When we first found Pluto, way out here in the outer parts of our solar system, I've brought up its path as well, out beyond Neptune. We thought it was the only thing out here. But then in the late 1990s and early 2000s, our telescopes got better and better, and astronomers started finding some other objects. Now, most of these were small, icy objects, but some of them were actually quite large. And so I'm going to go ahead and bring those up as well. These are what we call trans-Neptunian objects, or sometimes we call them near the Kuiper belt is what we call it out here. So you might have heard of both terms. And so we realized Pluto wasn't the only thing out here. Pluto's pretty small. It also has this irregular orbit. So maybe we need to recategorize it. So they decided, okay, we need to really define what a planet is. And so they came up with 3 criteria for what we categorize as a planet. 1, it needs to orbit a star. Well, Ceres and Pluto both orbit the sun, so check. 2, it needs to be large enough, massive enough for its own self-gravity to be strong enough to pull itself into a round or spherical shape. Well, both Pluto and Ceres are both round, so check. And 3, it needs to have cleared its path. It needs a relatively clear orbit. Well, Ceres goes right through the asteroid belt and Pluto goes right through the Kuiper belt. So neither of them have a clear orbit. So we realized, okay, maybe we need to come up with a new category, and that's where we came up with dwarf planet. So both Ceres and Pluto are actually dwarf. So this is a great story about how we look out into space. And as our technology gets better and better, and the more we learn about our universe, the more as humans we like to categorize things. And so our definitions may sometimes change, but it's all based off of the data that we are seeing out in space. In fact, everything you're seeing today is based on that real science data. Okay, well, I'm going to go ahead and turn off some of these objects because they tend to slow down my planetarium software, and we still have quite a bit to go. Because if we were to travel from one side of Pluto's orbit to the other, that would be 10 hours to travel at the speed of light. So it's 10 light hours across. And let's recap. Remember, the sun is 8.5 light minutes away, and the moon is 1.5 light seconds away. So we haven't even traveled as far as light travels in a day. But even actually way out here, we can check in on our human influence. We can see how far our spacecrafts have gone. We'll start to see the paths of some of the fastest and farthest spacecrafts have gone. We have Voyager 1 and Voyager 1 and 2, Pioneer 10 and 11 that were sent out in the 1970s. And more recently, we have New Horizons, which was sent out to Pluto, that went by Pluto in 2015. And again, even this far out, our fastest and farthest spacecrafts have gone. They haven't passed how far light travels in a single day. So we need to continue our journey because remember, we're going to the edge of our universe and back, and we're still just within our solar system. And we'll start to travel the distances of light years. We'll see some of the stars in our own galaxy. Now, the closest star to us, well, beyond the sun, is about 4 light years away from us. That's saying it would take us 4 years to get there, traveling the speed of light. And even way out here, as we're getting many, many light years away, we can check in our human influence one last time. I'm bringing up kind of this sphere. And it's hard to see right now until we actually go outside of the sphere of how far our radio signature has gone. Now, what exactly is a radio signature? Well, our first radio and television signals that have gotten out into space, that have been able to escape our atmosphere, have been traveling since about the 1930s. So this is a sphere with us in the center and about 90 light years away from us in all directions. And this is how far those radio signals have traveled out into space, which is kind of interesting. So if we look at this radiosphere, we can also look at how many planets we have found outside of our solar system, what we call exoplanets. And now we have a ring around every star that has at least one exoplanet around it. Now, if we look closely, we can actually see some of those exoplanets are inside that radiosphere. So who knows? Maybe there's somebody listening to Nat King Cole. That'd be pretty neat. But we still have quite a bit of distances to go. Because again, we are still inside our own galaxy called the Milky Way. And as we zoom on out, I encourage you to keep an eye on that radiosphere. See how long it takes for you to be able to keep an eye on it or maybe lose it. And as we zoom on it, we can actually start to see the bigger picture of our galaxy, or at least what we think it looks like. Because again, we haven't traveled outside of our galaxy, but based off of mapping our galaxy, we know that we have a beautiful starred spiral galaxy. We see these beautiful arms, and we are about 2/3 of the way from the center of our galaxy. That's made of gas and dust and stars. And right at the center of our galaxy are a bright group of stars and are very close together. And if we could actually see past all those stars right at the very center, you would see, well, basically nothing because there's a supermassive black hole at the center of our galaxy. And that black hole is about 4 million times the mass of the sun. So I'm actually kind of happy that we're about 2/3 of the way out. Okay. Can you still see that radiosphere? Go ahead and point towards it. You're all correct because I have no idea where you're pointing. But I'll go ahead and use my cursor. And right at the tip of my cursor, you can see that radiosphere. That's our little corner of the galaxy, if there really is a corner in a sphere or a flat disk. I don't know. That's starting to get existential there. All right. We still have plenty of spaces to go because we've just gone outside our own galaxy, but we now get to see other galaxies. Now, every dot we see is not a star anymore, but its own galaxy with its own billions, trillions, and sometimes even more than trillions of stars. Sorry, I got a little lost there. And the colors of these galaxies may make it seem like somebody accidentally spilt some cosmic Skittles in the universe. These aren't the actual colors. These are actually showing the different densities and maps of the galaxies themselves. And as we kind of rotate around now what is our universe, you might just see something a little bit strange. There's kind of two phenomena that we can point out right now, and it's all based of how we are mapping our universe. One is you might notice that our universe kind of looks like a bow tie or butterfly shape. As cool as it would be that our universe would be a shape of a butterfly, it is not. It is our own mapping system. Now, remember when I told you that our galaxy was made of gas and dust and stars? Well, that gas and dust actually blocks our view, and so we can't see past it. Now, we're getting better and better technology, especially with the JWST telescope, but it still limits us on what we can observe. And so these areas that we don't have mapped are because we can't see past our own galaxy. We're pretty sure there's galaxies there. It's just we haven't mapped it yet. So because we haven't mapped it, we're not going to show you it. Remember, we're showing you everything that is based off of real scientific data. The other thing you might notice is that it looks like we are the center of the universe. Again, this is because we are making the map. We are looking out all around us and kind of standing still in a sense. If we were to go to any one of these other locations in our universe, go to another galaxy, and we were making the map there, it would appear as if we were the center of the universe. As far as we know, there's actually no center of the universe at all. All right, we still have a little bit more to go, and we're starting to get towards the edge of the universe. And we're starting to see some of the earliest objects in our universe, what we call quasars. These orange dots show the locations of the bright cores of the very first galaxies. And I do mean earliest because any time that we are looking out into space, we're kind of time traveling in a way. Because of the light of these objects have to travel so far that by the time it travels all that distance and gets back into our telescopes, we're actually seeing the light of those objects as they were in the past, not how they look today. So, for example, remember when we were talking about the closest stars to us, about 4 light years away from us? That's how they looked 4 years ago, not how they look today. So we are seeing the universe as it was billions of years ago. And because of that, there's only so far we can travel. There's only so far we can see in our universe. And that edge now appears around us. This is what we call the cosmic microwave background, or CMB. Now, if you had a radio telescope that could see in the microwave range of light, and you could see this everywhere you looked in the sky, you would actually be able to pick it up. In fact, the first radio astronomers were really confused because they thought it was actually interference with their telescopes. But soon they realized it was actually something they were seeing out in space. This is a few 100,000 years after the Big Bang would have happened. So you can kind of think of this as our baby picture. But since this is the edge of everything that we can see, means we got to start heading back home. So as we zoom on back home, I want to remind you, if we were that far out and actually traveling the speed of light, it would take us 13.7 billion years to get back home. But thankfully, we do have our planetarium software, so it's only going to take us about a minute. And as we zoom on back home, all of this that we have looked at so far, all these stars and galaxies in a cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. There's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it, especially at the edge of galaxies. And we call all these things dark energy and dark matter because, well, we're not quite sure what they are. But we do know that they make up 96% of all the things in our universe. And that may make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we are one tiny dot, but look at all that we have found, almost entirely by looking through telescopes. So there's a whole lot more for us to discover and a whole lot more for us to learn. And that's what makes it a wonderful time in human history. That we're not just able to learn about these things, but show them like this, a map of our cosmos in 3 dimensions. And we're only just starting to unravel the true nature of our universe. But we're only just starting to unravel it. The rest, well, that's up to the next generation of scientists back here on planet Earth. Well, we're heading back to that third planet from the sun, the only place in all of this that we have found life. And that's pretty incredible to think about. So welcome home, everybody. And I want to say thank you for joining us for our tour of the universe. If you would like more information about some of the things that we talked about, you can find those links in our chat box. Also, as I mentioned, we are using a planetarium software, and this planetarium software is called OpenSpace, and it's an open source planetarium software that you can actually download at home yourself. If you like to leave us some information of how you liked the program, we greatly appreciate it. But finally, we are back home. So thank you, everybody, and have a good night.